In this video, we discussed the concept of unconditional convergence of series in Banach spaces. And this is meant as a prelude to a discussion of unconditional basis in Banach spaces, which is part of our attempt to understand which bases in Banach spaces behave to a large extent like orthonormal basis in Hilbert spaces. So what is unconditional convergence? Well, we say that a series in a Banach space converges unconditionally if all of the series of the form sum of epsilon and xn, where epsilon is any choice of plus or minus one you want, still converges. So with the choice epsilon n constantly equal to 1, you have your series, but you're asking for a whole lot of other series to also converge. Now, if the Banach space is finite dimensional, then this is really the same thing as asking the series to not just converge, but converge absolutely, right? So if we were to think of x to the r, and I look at the series where xn is minus 1 to the n divided by n, now this series will be the perfect example of something that converges but in r, but does not converge unconditionally, because if I'm get rid of all the minus 1 to the n, multiplying the odd one by minus 1, then I get the harmonic series which diverges. Now, on the other hand, if you look at a Hilbert space and you take its canonical basis, so or any orthonormal basis really, and then you look at the series en sum of en divided by n in this Hilbert space, this will converge, and this will also converge unconditionally, because really the norm of that will be the sum of the 1 upon n squared, and so it doesn't matter if you multiply your 1 upon n by plus or minus 1. Now notice that this is not the same thing as asking for the sum of the norm of xn to converge. If you ask for that, this is stronger than being unconditionally converging, but the converse is not true, right? If you look at this example that I've given here, you have a series that converges unconditionally in the Hilbert space L2, but it's not normally convergent. The sum of the norm is not converging, because the sum of the norm here will be the harmonic series, the sum of the 1 upon n. So in finite dimension, unconditional convergence and absolute convergence are the same. In infinite dimension, we have at least 3 notions of convergence. We have standard convergence, we have unconditional convergence, that is obviously stronger, and then we have normal convergence here, which is even stronger. Now, normal convergence for our purpose would be too strong, right? Because you would miss the fact that something like that, some decomposition into an orthonormal basis in a Hilbert space with coefficient 1 upon n, does converge, and in fact even converges unconditionally. So we are trying to capture this sort of nice properties of orthonormal basis that, at the very least, if you look at a diagonal operator with respect to an orthonormal basis and all of the entries of that diagonal operators are just plus or minus 1, then this operator will have to be bounded. And really we're shooting for something similar when you look at diagonal operators with respect to a Schauder basis in a Banach space. Okay, now what we're going to do in this video is we are going to see in which way this notion of unconditional convergence in a Banach space works like absolute convergence, which is unconditional convergence in finite dimension. And this is the purpose of proposition 11.2, and it says the following assertions are equivalent. So converging unconditionally, so being able to multiply xn by plus or minus 1 and keep convergence, is really the same thing as asking for every subsequence, or more precisely the series with general term, any subsequence of the xn converges. And this is also the same thing, let's have a look at 4 because it makes more sense than 3 maybe. It's the same thing as saying that you could permute all of the natural numbers, take any bijections from the natural to the natural, and the series will still converge. So another way of thinking of unconditional convergence is that it's a form of convergence which is insensitive to the order in which you're summing up your series. You might remember the striking result, in my opinion, in finite dimension, that if you have a series that converges but does not converge absolutely, you could reorder the term such that you get something that converges to whatever number you want. So this ability to converge, even if you change the order, is something that is very specific to series that converge unconditionally, or in finite dimensions, that's to series that converge absolutely. Now, let's just mention 3 too. So 3 is saying that if you look far enough into the natural number, it doesn't matter where you look, any finite set of natural numbers above capital N will be such that the series restricted to that set is small enough. So we know, of course, that if we have a series that converge, if you look at you have a Cauchy sequence when you look at partial sum. So if you were to take f to be a sequence of natural numbers from capital N to some capital M, if capital N is large enough, then this would have to be small. But this is telling you that you don't have to pick consecutive natural numbers. You can pick any finite f as long as it's far enough into the natural, and you will have this property. So this is a reinforcement, if you want, of the Cauchy criterion, which already hints at the idea that it doesn't matter if you reorder the natural number when dealing with a unconditionally convergent series. So this is what we're going to do first. We're going to prove in this video proposition 11.2 to understand the different ways of that a series converge if it is to converge unconditionally. Okay, so let's start the proof of proposition 11.2 with the implication 1 implies 2. So we have a series that converges unconditionally, and we want to say that the series of its subsequences converges. So let's take a subsequence. The subsequence of xn and sum of xn converges unconditionally. Okay, so what do? Well, we just pick an appropriate choice of sign. So we're going to pick epsilon n equal to, okay, I want it equal to 1 if n is equal, well, if n belongs to the set of all nk's. So if it is in my subsequence, n minus 1 otherwise. And then you should notice that 1 plus epsilon n over 2 is going to be equal to what? It's going to be equal to 1 if n belongs to the subsequence, and it's going to be equal to 0 otherwise. Okay, so now that means that whenever you look at a partial sum of your subsequence x and k equals 0 to n, for any capital N in n, then what you're going to find is that there exists a, let's call it m in n, such that this is equal to the sum n equals 0 to capital M of 1 plus epsilon n over 2 times xn. Right, you just have to pick the m such that x capital M is equal to x little n subscript capital N, such that you get all of the terms in this series through that series where the 1 plus epsilon over 2 just give a 0 whenever you're not in the subsequence. Okay, so because we have that, then the series on the left is going to be Cauchy, or the sequence of partial sums is going to be Cauchy if and only if the sequence of partial sums here is Cauchy. So the fact that sum of epsilon n, xn, and sum of xn itself, these two things converge. This implies that the sum of the x and k converges. Okay, and that proves that 1 implies 2. Now let's go in the other direction and prove that 2 implies 1. Right, so for 2 implies 1, I know that over every subsequence I'm converging, and I have to show that this implies unconditional convergence. So I give myself a choice of signs. So a sequence of plus or minus 1s. Okay, and then you define a set A to be the set of all those n's for which your epsilon n is plus 1, say. Okay, now there's two possibilities. Either that set is finite. Okay, but if A is finite, then sum of epsilon n xn does converge. right? Because throwing away finitely many terms is equal to minus the series sum of xn, which we already know converges. Right, now what happens if a is infinite? If a is infinite, then you can rewrite a as a increasing sequence of natural numbers, right, with nk increasing. Because it's in bijection with n. And you know that the sum of the nk converges. That's your assumption too. And because this converges, well, you can notice that sum of x and k is equal to, which we know converges, is equal to the sum of 1 plus epsilon n over 2 xn. Right, because 1 plus epsilon n over 2 is going to be equal to 1 whenever you're in A, and it's going to be equal to 0 whenever you are not in A. So it picks exactly the nk terms in the sum. So, okay, so the sum of 1 plus epsilon n over 2 xn converges. But since the sum of the xn themselves converge, we have that the sum of the epsilon n xn has to converge too. And that proves 1. So we have proven that 1 and 2 are equivalent. Now let's have a look at the equivalence between 2 and 3. Okay, so for 2 implies 3, we are going to work by contradiction. And we start by assuming that there exists an epsilon such that for all n in n, there exists a finite set Fn, which is further into the natural numbers than the first capital N element, and such that the sum of xn on that finite set F capital N is greater than epsilon, right? Negating 3. Okay, and now from there we want to construct a subsequence x and k such that the sum of the x and k is not Cauchy. So here is how you do it. You first pick n1 to be 1, let's say, and then inductively we define nk plus 1 to be the maximum of the f and k plus 1 for all k in n. Right, so given 1, there exists an f1 such that this holds, and then we pick n2, the maximum of the elements in this f1, and then plus 1. Now the reason why we do that is to ensure that these sets that we are picking, the f and j's, are disjoint. So whenever I have a j and a k that are not equal, I have that f and j intersected f and k is non-zero. Is empty. Right, because I've constructed my sequence of natural numbers capital Nk by picking the nk plus 1 element above the maximum of the f and k, and so my f and k plus 1 is going to start somewhere above capital Nk. So I have this disjointness of my f and j's. Now, because they are disjoint, if I take the union of this disjoint set, f and j, j running between 1 and infinity, it's a union of disjoint subsets of n, and it's a infinite union, and every set starts at a point which is further on the natural on the set of natural numbers than the maximum of the one preceding it. So this can be rewritten as a sequence nk, k in n, for some increasing sequence. Sequence nk. Right. Okay, you just pick all the elements in Fn1, and then further than that, you've got all the elements in Fn2, and so on and so forth, and that sequence is increasing. Now, what we get then for that subsequence is that you can go as far as you want, and you will always be able to find two numbers, let's call them k1 and k2, above that m, such that the sum of x and k between k0 and k1 is exactly the sum of the xn in some set f and j, so for some j large enough. Right? You can give yourself any m large enough, and you can identify the elements of that subsequence with the elements inside some f and j. Yeah, but the f and j's have been defined in such a way that you can take them, well, wherever you take them, doesn't matter how large j is, these sums are always greater than epsilon. So this is telling you that the series here cannot be, well, the partial sums of that series cannot be Cauchy, so this theory cannot converge. That is, 2 doesn't hold, and so by contrapositive we've proven that 2 implies 3. Okay, so let's look at the reverse direction. 3 implies 2. Let's take a subsequence of our xn. Okay, and we have by 3 that for every epsilon there exists a capital N, such that for every f that is a subset of n, but that starts after capital N and that is finite, the sum of xn over that subset fn is more than epsilon. So we just have to pick our f n appropriately. And how are we going to do it? We're going to say that given n in n, and let's say k1 greater than k0 greater than n, I'm going to define a set that I want to call whatever, f k1 k0 n, I suppose, to be the set of all those nj's where j runs between k0 and k1. Okay, so then what do I have? I have that for every epsilon there exists an n in n such that for all k1 greater than k0 greater than n, well, on this finite set I am small, so the sum for j running between k0 and k1 of x and j is smaller than epsilon. That is literally saying that the sequence of partial sum of the x and k is a Cauchy sequence, and therefore the sum of the x and k has to converge. Okay, that proves 3 implies 2. Now let's have a look at 3 implies 4. So we've proven now that 2 is equivalent to 3 and 2 is equivalent to 1. We just have to prove that 3 is equivalent to 4. So in one direction, going from 3 to 4, it's again just a matter of picking our finite sets appropriately. So we start with a bijection. Okay, and then what do? We choose, given a n, in n we define f and sigma to be the set of all those sigma j, where j runs between k0 and kn. Should have called that f and whatever, sigma k0 k1 for k0 greater than n and k1 greater than k0. And then applying 3, we have that for every epsilon there exists an n, such that for this particular choice of sets, therefore for all k1 greater than k0 greater than n, the sum j equal k0 to k1 of x sigma j, which is exactly the sum of the xn on the set fn sigma k0 k1, is smaller than epsilon. That is saying that the series x sigma n with general term x sigma n is Cauchy and therefore converges. Okay, now the last thing we have to prove is 4 implies 3. Okay, so for 4 implies 3, we work by contradiction. And so we assume that there exists an epsilon and there exists a sequence f and j of subsets of n that are such that the minimum of the f and j, so subsets that are finite, and such that the minimum of the f and j is always greater or equal than nj, and the sequence nj goes to infinity. All right, so we pick finite set further and further such that we still have that the sum of the xn and in f and j is greater than epsilon for all j. Right. So, okay, we can do that for every j. And so what we're going to construct is a bijection. So we pick a bijection that is such that what? Such that the inverse image by these bijections of f and j is of the form nj till nj plus mj for some mj in n. Okay, and we do that for all j in n. And so we just reorder the f and j such that they are just nj and j plus 1 until something. So then what have we got? We've got that the sum of x sigma n, so the sigma n's will be exactly those n's that are in nj. So if I sum that from nj to nj plus mj, well, I literally get the sum of the xn when n is in f and j, and I know that this is greater than epsilon. And now that means that my series of x, sum of x sigma n, cannot be Cauchy, and so it cannot converge, which proves that 4 doesn't hold when 3 does not hold. And that concludes the proof of this proposition 11.2, which tells us that unconditional convergence is the same as the convergence of every permitted series, and it's the same as the convergence of the series of every subsequence of the sequence we started from.